Can everyone hear me well? So, last talk of the day, right? I have a super long talk and even longer introduction, so out of compassion, I will compress what I can. I'm Pablo. I work at PyTorch in the transformers team, and I'm an ML engineer. But I wasn't always like this. I used to be a physicist. I'm a physicist by training, and I switched to ML around 2015, 2016. I would like to start there, back in the prehistoric times, where there were many frameworks, many kinds of ML, many kinds of things that people were calling AI at the time, and frameworks were being born and died. I worked with Piano, I worked on Café 2. These words might mean something to you if you have grayer hair. Myself, many people were jumping framework to framework, and Torch really changed a lot here. And in 2017, it was attention is the limit. In BERT, there was, in 2018, there was BERT, not the other way around. When BERT came out in the industry, it became something that was a no-brainer. We need to have these in our stack somewhere because the embedding of our products are going to be amazingly well for recommender systems and so on and so forth. But that wasn't that easy to implement. I worked in the industry back then, and reproducibility, which was mentioned before, was incredibly hard. And one of the things that made a change here was PyTorch pre-trained BERT, which self-explanatory name, which is the previous name of the transformers library, the initial name of transformers. This was a simple interface. It was relying, Torch was relying on dynamic graphs, not static graphs, that you could debug. And this library, built by many amazing people, was designed with opinionated paradigms. And one of them was hackability. You need to be able to take apart a model by its defining components and make itself your own and redefine it and be able to train it how you want and so on. So I'll skip a bit here on the dynamic graphs and the rest, but that was the idea. You want to have a new paper that comes out, because after BERT, then people were like, oh, so encoder models are nice, but what about encoder-decoder model? What about just decoder models? And now we are here, and other kind of model. So you could do live debugging. You don't have to recompile your model and then hope that it works. And you can just relaunch it, add a PDB somewhere, and look at what is the model doing. That was insane. Because before it wasn't like this. So the iteration cycle in development teams shortened massively, from weeks to hours. I'm not even exaggerating. And but that is only possible when you have opinionated decisions made on library. I love paradigms, and transformers is based on many. I'll go over two: one model, one file. Why it matters? You have everything defined in one place. All the components of the model, the forward pass, how the loading of the parameters is defined. You don't have any cross-file inheritance maze. Everything is just there. The attention of this model is here. The MLP of that model is there, and so on. It means that when you want to integrate a new model, the reviewers have reference implementations, and they just have to look at what's different there and decide if it's mergeable or not, which makes it much faster. Because second paradigm of critical importance was backwards compatibility. If you want results to be reproducible, okay, at time t, cool, but what about time t plus 1, t plus 10? Can you rerun this model in 10 years? Can you rerun this model in 20 years? Can you be sure of that? In order to be at least confident in that, you need to make everything backwards compatible. So once you define an API, you are not allowed to change it ever again. Of course, that's a really hard decision, but it allows you to just build up and stack models on top of each other, right? So that allowed transformers to grow massively and hold and define more and more models. The scientific community was able to build and contribute when labs and companies have a great new model. We've heard several today. They were able to just add it to transformers, and then it becomes the definition there. And it also fed back into PyTorch, which we lean on extremely heavily, of course. And the adoption fed back into both ecosystems. Of course, there's two issues there. Because you have strong paradigms and strong opinions on that what should be in the library or not, it means that you have a lot of pressures on maintainers. Because you have suddenly a lot of duplicated code. Llama, because I said everything is in one place, but it means you don't want to do cross-file inheritance, so everything now is super duplicated. And you have less Pythonic modularity. Having these constraints harms kind of the Pythonicity of what you want to achieve with your library. And so I'll go over a few things that we achieved recently to upgrade these paradigms to modern times and to be able to sustain the acceleration of model development and AI development. Okay, good. So one thing that I'd like to promote is the modular transformers. It's an API where you define a modular file which is not runnable, and this is a real-life example, the GLM model. When it came out, we looked at it, and models are defined not only by their architecture, they are defined by their training mix, by how they were trained, how they are evaluated even, and so on. But the architecture should be written once and for all somewhere, and be defined once for all somewhere. And transformers is the support for that. Because here, notice, okay, GLM, the MLP of this is actually 5.3 MLP. So you can write it like this. The attention is llama attention, but there's a slight change. Okay, write this slight change. And the general thing, GLM for causal LM, mimics llama for causal LM. So it means the forward pass and everything should be compiled in the same way. So then you write exactly that, run a command, and it becomes the complete code, which is runnable. So it becomes the modeling code, which is automatic. It means that reviewers can only look at the previous, have only to look at the previous slide, which is defined by the difference difference with existing models. So I redefined, what did I just do? I just redefined inheritance. But actually we couldn't be using inheritance because of the paradigms that we were using before. So now, currently this is mostly used to refactor models and define them more clearly. But the research community can also use that if you have like a great new idea, oh, layer norm, this kind of layer norm should be amazing. So I want to define a new model. It will be llama 4, but I'm just going to change that layer norm. Then just do that, and it will automatically make it supported in transformers. Okay. And I will go over a couple other features recently. Since everything relies on resolution is okay, it's fine. Everything relies on PyTorch. Everything relies on nn.module. One thing we can do is trace every single activation that goes through a model. Maybe your question is why would you do such a thing? It's because when you implement a model, I mentioned reproducibility in the beginning of the talk. You want to make sure you're not messing around with the epsilon of an alpha layer norm, or the activation function maybe is not relu, is jelu, or silu, or swilu, or something. Or you know what I'm getting. So when you do that, you can output. This is also a very simple declarator you add to the model forward pass, and it will output all the logits to a JSON file, a very simple text file, which you can put side by side. So you have your two implementations, you put the two of them, and you just look. And you will find, it will jump out in the diff where the logits start to differ. It's just a simple tool, but having everything that is defined like this with nn.modules allows you to do such small, helpful debuggers. And this was really a lifesaver for me, at least in the last couple sprints. So, you know. And another thing is detensor was mentioned, distributed tensor, recently. I mean, by recently, I mean 20 minutes ago, maybe a bit more than that. So it's distributed tensor. It's a way to, it's a framework that allows you to do tensor parallelism among among other things. The thing is, when you want to define operations such as column parallel, so linear projections here, when you want to split them across ranks, you will have to change the modeling code before. So column parallel, row parallel for projection. And instead of doing that, now we have something that relies heavily on the tensor, where you just include in your configuration a regular expression here that defines what kind of TP plan, what kind of tensor parallel plan you want for each layer. So you just write that. The modeling code, once again, the architecture, the core skeleton of your model does not change. What changes is just the configuration file. You just do that, and it will map automatically and do the initialization, the dispatching, everything automatically within Transformer in the backend, thanks to PyTorch. So just one small change on JSON, the 100V scout, for example, can be distributed on AGPU with natively on transformers. So that's pretty cool. That was also in the Llama 4 sprint. Again, reducing iteration cycle. Now what we have is a smart cache allocator. When you load a big model, now it minimizes the number of CUDA mallocs. Before it was doing one single CUDA malloc for every basically piece of the model, and now we pre-allocate a lot in what we can. So 50 shards, 100V on the non-optimized file system. This is very much like running locally, doing it in less than 1 minute now. And before this, so if you tried like before April 3rd, would have taken you maybe 8 minutes. So it's pretty good improvement. If you have fast file system, it's even more better. So quite good. And there's why it works, why adoption grew. It's also because Python has a low entry bar. I know because I'm coding in Python. So it's hard to master, but you can enter into it and understand it. It's readable, and high-level semantics express low-level instead, which sounds good. And you have, so PyTorch rely on Atom, and you have Rust extension point. So you can still think, okay, I can do everything in Python and then rely on some stuff under the hood that will accelerate everything for me. Thing is, there's many things that we have to consider. Python is still a bit slow. There's the global interpreter lock is still a thing. Might change, but for now we don't know. And the code that comes from laboratories is not production code, it's research code, and just that changed the difference of culture between research labs and production labs. Just can lead to under-optimizations that themselves take time to fix. Most of these can be largely mitigated. One initiative we have in around Transformers, is kernel community operation. So basically, the idea is, and this is already existing, to have the kernels library and the kernels community on the hub. You can, because kernels are what make the difference in terms of making atomic operations faster right now. And the idea is, for example, here, this activation function, you can get it from kernels community/activation for /something, I forgot something, it's a JLU activation. And just load it, drop it in a decorator in your running code, and the modeling still does not change, but you leverage optimized kernels. And this allows you, if you want to build kernels, to build them, upload them on the hub, and make them usable natively on Transformer model. Okay. So yeah, just summary slide. Yeah, and all of what I mentioned, it's a bit invisible, but it's mostly text models that were that I was mentioning. But of course, there's image. By image, I mean there's images, but also videos. There's audio. We had a really nice demo just before. And the idea is that Transformers has the same API always for every modality. And there's more and more models that come in, like really more and more models, each with specific processing, so we need to uniformize. And then again, thank you Torch, and Torch Vision, thank you Nicholas also, because as you see, this is processing speed of a single image, just a very simple benchmark, all benchmark being wrong and some useful, this is useful for me. And now Torch Vision based ops and Torch based ops are replacing Peel and NumPy transformation defaults in transformers, mostly because it's faster and faster. It's much faster. I didn't compute the ratio here, but with a simple calculation you can do it, and you can see that the right side is better. And this is very important. We have now faster image processing because of that. This is a past graph of contributions to transformers per modality. Currently, there's more than 300 architectures that are supported in transformers. The total and the text is overlapped, and this is as of April. There's more than 300. Actually, I'm probably missing a couple. I did this by a horrible Git parsing script. Image models are in red. They are growing and growing as we go. You can see there was an acceleration here. Here's just a deprecation cycle. There were a couple of models that were bolted initially that were not as important for the community. They were not downloaded, and they have been reduced a bit. But still, you can see that this curve is not slowing down at all. There's more models being added every week, every release. So we have new models, and the audio and video modalities are slowly but surely climbing as well. And there's not even action modality. I mentioned robotics earlier. That's also there. So, but these models, it's cool. Okay, these new models in transformers, even from research tabs, could be like, okay, my model is in transformers. I won the game. But no, the game just starts. It starts there because once it's in transformers, the elasticity can be reused by other members of the ecosystem and very easily. For example, our great friends at the LLM, they make inference extremely fast. They are known for that. So you can prototype with transformers. For example, here, ask to some Llama model, what's the future of AI, and do something that is extremely similar with the LLM by just specifying the model implementation transformers. Because transformers is now a backend of the LLM. So in theory, all models that are out in transformers can be Day0 supported in the LLM. But that's not just true for the LLM, that's also true for SGLang and thousands of other libraries. So I talked about all of these cool features around transformers. So going forward, what we're aiming for is centralizing the model definitions across all of the ecosystem. The idea is there. As I mentioned, we have more than 300. I think if we count correctly, it's around 340, 350 definitions of models in transformers. And so it means that if you use transformers as a backend, you can use any of these architectures out of the box. You don't have anything more to do. So yeah, and we grew and we are powered by PyTorch, among other things, but we are very happy that our friends at the LLM, SGLang, and others, they rely on us for that. And that as soon as the model is supported on transformers, which is usually day 0, maybe week 0, sometimes hour 0 or minute 0, if the stars align. As soon as it's there, it can be reused in Llama CDP, in TGI, in VLLM, in MLX, in SGLang, and so on. So that's it. I think I'm mostly on time. But yeah, the view on that slide, and most important is the bottom right part, that we aim to become this source of truth for model definitions. So thank you very much.